Now, one of the nice things we can do when we have this mass action quotient is plot it as a function of time so that we can follow a chemical reaction. So I'm just going to make a little plot right here, and I'm going to make a plot of something really boring like A reacting to form B. There's A reacting to form B. Now, as a function of time, I'm going to measure the concentrations of A and B. So for example, right up here, I'm going to start off, and that's the concentration of A to start. Over here, I have my concentration of B to start. And I'm going to allow this reaction to happen. Stop a second. What is the value of Q at this initial point here at time 0? Well, because I've started with all A and no B, then the ratio of B over A is 0 over some amount, which means that at time 0 right here, Q is equal to 0. So that's my starting value, Q equal to 0. Well, I'm going to let the reaction happen. Since the reaction is going to happen so that A goes to make B, the reaction is going to head to the right. Now you might say, well, why can't it go to the left? And the answer is, how can it go to the left? There is no B to react. So the reaction is stressed to go this way. Not all that different than when we think about osmotic pressure and the fact that we have to move toward the less concentrated side. So the reaction heads off to the right. As it heads off to the right, the amount of A is going to start to go down. And we'll learn later why it is that it goes down very often in this sort of exponential way. What is B doing at the same time? It is forced by stoichiometry to be increasing in a proportional amount. If I start with 100 A's and an A goes away to make 99, then I've got to make one B. If 14 A's go away, I have to make 14 B's. So the curve that I'm going to be creating here is going to be a curve in which as the A decreases, the B increases with exactly the same shape, but going in the opposite direction. If I stopped and I calculated at this point right here, or at this point right here, or at this point right here, what Q was, what do you think I would be getting? Well, A would be getting smaller and B would be getting larger, so I would be watching Q grow. It started at 0, it becomes more and more and more and more and more. And it keeps on trucking along. At this point right here, interestingly, this is the point when the amount of A and B happen to be exactly equal to each other. And if I put them into my expression for Q, where Q is B over A, and I started with 100 A's, that would be 50-50. In other words, Q would be equal to 1 at this point. And the reaction keeps going. At some point, though, I notice that nothing's happening. That right about here, I made about 80 B's and 20 A's. And then about 5 minutes later, it was still 80 B's and 20 A's. An hour later, 80 B's and 20 A's. 3 years and 6 minutes later, 80 B's and 20 A's. It would turn out that Q at this point was equal to 80 over 20, would be equal to 4, and guess what? That point right there on that curve where the slopes have gone to 0 is the point where I have reached this thing called chemical equilibrium. And that is the point where Q has become K. This right here is an enormously important and insightful curve. This is a reaction profile showing you concentrations as a function of time, showing you how Q, the mass action quotient, changes over time as you fall down a hill. I'm no longer measuring delta G as I fall down the hill. I am measuring concentrations as I fall down the hill. And as I measure them, Q goes from being 0 to something larger to it's right about 1 right here. And then right about here, Q becomes 4, and it doesn't change anymore. This is exactly the same sort of idea as what I was showing you when I was drawing you a potential energy curve involving free energy, and we were watching this hill here. As delta G changed, and I fell down the hill till I got to where delta G was equal to 0. Now, it's Q that's changing as I fall down the hill and I get to K.